Hello and welcome back to Unit 9. In this part of Unit 9, we're going to look at conservation of momentum. And to motivate this, we're going to think about Newton's third law. So if I think about Newton's third law, it tells me that the force from one object on the second is equal and opposite to the force from the second object on the first. And that's why we have the negative sign here as a reminder that they're opposite direction. Okay. Now we're going to make an assumption. And that assumption is that these are the only forces that matter. Okay. So because these are the only forces that matter, that allows us to say that these forces cause the accelerations on these two objects. And we've applied Newton's second law here to that. I'm now going to plug in the definition of acceleration again as change in velocity over change in time, again in the differential form. And I'm going to move the masses into the derivative. Okay. And again, we have an assumption here. This assumes the mass is constant. Okay. Okay. And now I can define this as change in momentum 1 over time. And if I bring the right-hand side over to the left and pull the differential out in front, I find that d by dt of the combined momentum of my two objects, P1 and P2, equals 0. And the result of that means that P1 plus P2 has to equal a constant. Okay. In other words, it's conserved. The combination of the mass of my two objects has to be the same number everywhere, therefore it is conserved. Now, what does conservation of momentum actually, the statement of it say? It says, in an isolated system, the total momentum of that system of objects is conserved, it's constant. Often this is written as initial momentum equals final momentum, P initial equals P final. And usually we have more than one object, so that would be the initial momentum of object 1 plus the initial momentum of object 2 has to equal the final momentum of the two objects combined. Now there are a couple of pieces here. First off, what does it mean for something to be isolated? Isolated means no net external forces. So remember when we said F21 could be written as M1A1, and I made this argument that these are the only forces that mattered in that derivation? That's what it means. There's no net external forces. The only thing causing the interaction of these two objects, the only force that results from the interaction of these two objects is what's causing the change in momentum of each object. The other piece of here was system. Okay, system. What is a system? Well, it's simply the collection of objects you're looking at. A system can be a single object or it can be multiple objects. But if you're only looking at a single object and its momentum changes, then there has to be a net force on it, in which case it's not isolated. So, as an example of that, if I push on an object, say a ball, and get it rolling across the floor, eventually that ball will slow to a stop, assuming it doesn't hit a wall or something else first. Okay. So why does it slow? Well, it slows because there's an external force on it. It's not isolated. Okay. That external force is friction. So where does the momentum go? Well, it goes into the earth in some way. Maybe it goes into a change in kinetic energy of the floor that it rolled across, the molecules in the floor that it rolled across. So it would cause the floor to heat up a little bit. Maybe it actually pushes the molecules around and causes a physical displacement of that. More like if I roll a ball in the sand, you can see a track of where it went. Right? Where does it go? It goes into the floor somewhere. If we wanted to isolate, we would need to be able to include all those aspects of the surface it's rolling across in our system in order to isolate it, which is really tough. This concept of conservation of momentum is what allows a rocket to work, or what allows a balloon to fly across the room. If we think about a rocket or a balloon, what do we have? We have something. I'm going to draw my rocket here. There you go. It exhausts a gas. So we have the gas going one way, which causes the rocket to go another. And because the rocket and the gas were one unit beforehand, they had a certain momentum. Now that I'm pushing the gas out one direction, that will cause the momentum of the rocket to increase in the opposite direction. Same idea with the balloon flying across the room, except it's just air being released. We're going to be applying conservation of momentum in the next couple of units to collisions. Collisions can be divided into two different types. If we have an elastic collision, it conserves both energy and momentum. If we have an inelastic collision, it conserves only momentum. And there's an entire range of inelastic collisions, some that conserve energy better than others. So if you have a perfectly inelastic, that means it conserves energy as little as possible, resulting in the largest change in energy from before to after. This concludes this part of this unit.